Happy Garbage Day! Happy Tuesday to everyone else who doesn't celebrate Garbage Day. I have homework open here so that we can answer any questions that you have. I heard from Vladimir that he had a busy office hours this morning and that there were a couple particular things that folks had in common in terms of what they were asking about the probabilities of finding things. So in the sections that are using logit links, you should be able to compute a predicted probability from either the model parameters, if that's what the question is asking, or for a predicted kind of response. So for instance, for this item, what is the probability of not being endorsed conditional on theta? So what model parameter, for instance, would tell me about not being endorsed? And I see question 19, we'll talk about that in just a second. What does that sound like? A model parameter that's related to the lower category? Yeah. So if you can find the threshold, that gives you the logit of not being endorsed. So then how do we get from the logit to the probability? Yeah, 1 over 1 plus e to the not logit. So if you put minus 1 inside the parentheses, or the version that I usually say is e to the logit over 1 plus e to the logit. And if you're trying to describe that in a technical paper, what is that called? To unlogit something back into probability. Inverse link. Yep, and that's the general term, and I believe it's the inverse logit link or inverse logistic link in this particular case. So yes, the not being endorsed conditional on theta 0, that's a threshold. So I warned you at the beginning of this that a lot of these numbers are actually vocabulary drills. So yes, exponentiate would be to get from logits down, like down 1 level. That would give you odds or odds ratios, and then 1 more down to probability is the full inverse link. So yes. Dan has a question on 19. What is the largest trait value of those given for which the predicted reliability is greater than 0.9? So reliability is something that you have to compute first, and that is computable from what? Information, yeah. The formula is information divided by information plus 1. That is located in several different spots, including the example handout and the example spreadsheets that go with the example handout. Question 21. What is the variance of the estimated factor scores as given in the M+ output? Okay, so that one could possibly be a difference in operating system giving you a different answer, because Vladimir and I ran into this when we were testing the answer key. I had a difference in the 3rd decimal place relative to what he had running the exact same analysis on the same data. So if 21 is not working, I would try plus or minus 0.001 for your answer and see if that takes it, and then you'll have my sincere apology if that is the case. But it's kind of crazy to me how you can get differences even when you're literally doing the same thing. But the version that is, we tested it on the version that is on the virtual desktop, and so that's what the answer key is tied to try and minimize that, since that's what most of you have. If you're running your own copy of M+ on a different operating system, you may end up with very slightly different results. Okay, what was the other one, Vladimir, that you said?
There is something else, Lisa.
Okay. Okay, I have a request to repeat something, and then Vladimir has another one. The logit to probability equation. It is e to the logit, so exp to the logit, divided by 1 plus e to the logit. That is in, let me pull that up. I can point you to exactly where that is. That would be in lecture 5a, amongst other places. Come back. When we talked about logits in the first place. Somewhere in here. Here we go. So for instance, to go from the conditional mean predicted in logits, e to the logit over 1 plus e to the logit. Does that help? Yes. Okay, so this is lecture 5a, slide 13, and it's in a few other places too. Okay, Vladimir, you were going to say.
Yes, sometimes M+ doesn't save the things needed to perform the likelihood ratio test using the WLSMB method.
Okay.
So I think that we had that problem in our last class. What can we do in that case?
Okay, so the question was, or the issue is, when using WLSMV, you have to tell it to save the results of the more complex model and import them essentially to get the difference test for the less complex model. If that is not working, you may need to put an actual file path in front of what the file name is. Because I've discovered this, hey, come on, there we go. I discovered this the first time I taught this class here, that for some people, their paths exceeded the maximum length that the system would take. And so like M+ was throwing errors because it didn't have a place to send things to, like there was a breakdown in the communication, and that seemed to fix it. So if you're getting weird errors, put the full path to where you need things to go in front of it, and that may help. And if the path is too long, you may need to move your stuff closer to the root of the H drive so that there's not a bunch of folders in the way, making it longer. If that doesn't work, send it to me. Like if your stuff isn't running for no reason, send it to me and I will help you, okay? Our job here is to not get frustrated with poor technology. That's just an unfortunate benefit. All right, other questions on homework or other topics of review? Okay, then in terms of what is coming up as we continue winding our way through the semester, next Monday is due your revisions to homework 3, if you want to. You can get back all the points that you lost except those due to lateness. Those are not returnable. I do accept late revisions, but it's 1 point off for those. So if you don't have time to get it done, but you'd like to get it done eventually, you still have that option. However, I would encourage you to get the revision done so that I can grade it, because then homework 5 is coming up right after that. So whatever feedback I can give you hopefully will come in handy when you're doing homework 5, and that revision will not be due until the end of finals week. So something due every Monday until the end of the semester. That's how it works. All right, so no more on homework? We ready for a new topic? Yay! Can you pretend we're ready for a new topic? Okay. A little lack of enthusiasm, but I'm going to fake it. I'm going to fake it for all of us. Okay. I've got lecture 7 on deck here. So we are talking about, we're still in the world of measurement models, but we're heading towards the world of structural models in terms of complexity. So this topic is measurement invariance. That's what it's called when you estimate it in CFA models. It is called differential item functioning when you do the same thing in IRT or IFA models. And so I lumped them together because the concepts are the same, the processes are largely the same. It's just the language that gets to be a little bit different. So first off, big picture here. What are we trying to do? We're trying to ascertain whether measurement model parameters work the same way across different conditions or groups. So I have examples of language. So for instance, if you're giving a survey instrument and you translate it into a new language, one of the things that you would want to check is that the way that the items relate to their trait is the same across different languages. It could differ as a function of culture or something like that, but that would be a different reason. If you're interested in measuring people's change over time, the way that the items relate to the trait should be the same in order for the trait to be the thing that's growing. Repeated measures conditions, so if you're asking people to do a survey, for instance, you give it to someone's parents and you give it to their teacher. You might be interested in looking at invariance across those conditions for how the items function. So that's the general idea. It's, does the scale or do these items work the same way across different types of people or conditions that people might be in? So if so, then we say that the responses depend only on the latent traits being measured, and that's a good thing. If not, then it means that there's something else related to group membership that is causing people to answer the questions differently. And I say related to group membership because we don't know for sure what it is. Like gender is a proxy for different things. You know, country of origin might be a proxy for different things. So we have a label for it, but we may not know theoretically what that's about. These same issues are relevant in the IRT IFA world, but the baseline for it is anchored differently. So we talk about measurement invariance or measurement equivalence in CFA, whereas the phrase is differential item functioning, which means non-equivalence. So it's the same idea, just oriented from a different starting point as what it's talking about. So there's two different kinds of invariance, and whether or not these are met has different consequences. So measurement invariance has to do with the measurement model parameters directly. So we're talking about the factor loadings, we're talking about the intercepts, and the residual variances in a CFA model. In an IFA or IRT model, we would be talking about factor loadings, thresholds instead of intercepts, and not residual variances potentially. It depends on the estimator. As well as any residual covariances. Those would be considered part of the measurement model. So this idea that the measurement model parameters should work the same way is a precursor, a prerequisite to being able to make comparisons across groups. Because otherwise you don't know if it's the items that are functioning differently or if it's the trait that is different. And that's the distinction we're trying to make. So from this perspective, it is not okay if you don't have at least partial measurement invariance. That means the trait that you're measuring is not the same thing across groups, and it wouldn't make sense to try to compare trait levels if you're not talking about the same thing. It's like apples and oranges. So at least partial is the key here. How partial is partial? 1. At a minimum, mathematically, you need one item to have the same properties across samples. That, however, is a terrible idea. Like, you really got to believe that one item is the most awesome item ever if you're going to put all of your stock into that. Structural invariance, then, is a different type of question. Structural invariance has to do with trait differences that may, in fact, be expected in real. So do the groups have the same factor variances, or is one group more heterogeneous than the other? Do the groups have the same pattern of factor covariances? So are two factors more related in one group than another? Do the factor means differ across groups? Is one group higher in ability or more conservative or have more social capital or whatever your trait is? And at this stage, if you find differences, those are findings. Because if you have at least partial measurement invariance, you have evidence that says you're measuring the same thing, then these are real differences. So structural invariance may or may not be a part of your research question, but I'll show you how to do it, and I'll also show you how this shows up in the context of longitudinal data as what a growth model would be fitted for. Essentially, you can think of that as a structural invariance kind of question. Okay, how are we doing so far? Words? Concepts? Okay. Yeah, Erica, you're hidden from me. You're like perfectly behind my head, so I'll just keep doing this. So there's 4 students in front of me and 1 TA, so we got a small crowd today. And yes, I will be holding class on Thursday. I know a lot of you are going to AERA, but I'll be here. I get to stay home and parent, so if you miss the show, you can catch it on YouTube, the same as always. So options then. If your groups, and I'm talking about groups for the time being because that's the majority of invariance testing is in a group model, but if you have continuous predictors, I have a slide about that at the very, very end. So if you have independent groups, these people have nothing to do with each other, then you need what is known as a multiple group model. And the idea is that you are fitting separate models for each group, but you're doing it simultaneously. So you will literally have 2 different model statements, one for the reference group and one for each alternative group. And my examples have 2 groups, but you can have more than that. It gets a little bit tricky because there's a lot of permutations of group differences if you have more than that, but you can theoretically have more than that. So in terms of, I think the code is the same in Lavon, if I remember correctly. It's group equals as a new option on the variable statement within M+. In IRT models using full information, it's done differently via an option called known class. I'll give you an example of that later on. If you've heard of mimic models, this is an acronym that means multiple indicators, multiple causes. That is also a way that people sometimes decide to test invariance. The idea from that type of model is where you have a box in your model that is the group membership, and then that box predicts your trait or it predicts the items at the same time. And if the box has a significant prediction of the items beyond the trait, that's considered evidence of non-equivalence. However, that strategy doesn't allow you to test differences in the factor loadings. So it's an incomplete assessment of invariance, and I wouldn't recommend it for that reason. For dependent data, so for instance, if you have the same people measured repeatedly over time or repeated conditions, if you have dyads, so like two people from a relationship, parent and child, something like that, then the way that the models is set up has to be different. And I have a picture of that on the next slide. But the key idea is that all the indicators go into the same model so that you can add covariances between the factors that are repeatedly measured, as well as the items that are repeatedly measured. So this is what I'm talking about. I'll just show the slide here. This is from your textbook. Yep, figure 7.2 I borrowed. So this is an example of a latent trait of job satisfaction measured by 4 indicators at 2 different occasions. And so note the factors are correlated because logically speaking, how satisfied you are at time 1 is probably going to be related to how satisfied you are at time 2. That's the idea of dependency, meaning correlated outcomes from the same sampling unit more broadly. But note these error covariances up here. So this is a default in these sorts of models to allow the same item that's being repeatedly administered to have a covariance with itself. So what you said on item A at time 1 is likely to be related to what you said on item A at time 2, beyond the fact that your trait is also predicting A. So there's this extra common variance that is associated in these models. So this is the way that you have to do it if you have dependent data. Otherwise, if you end up with separate factor models that are estimated simultaneously, there's no way to put the covariances in. And so you would essentially be saying there is no covariance across the repeated factors or the repeated items, which is probably going to not be the case. So I will have an example of both kinds with respect to CFA so that you can see what that would look like. But we're going back to CFA for a while. How's that sound? No more thresholds for at least a week? No more probabilities, no more logits? So this is our CFA model, just to remind you what it looks like and the picture that goes with it. By the way, the same picture could be used for an IRT model with one exception. How would I need to change this picture if I were going to use it for an IRT model? What would I take away? Yeah, the e's. The error variances are not a thing in those models. I'd also have to do something about the stupid triangle because I would have more than one threshold per item instead of one intercept per item, but there are ways to notate that if you need it. Yep, no separate error variance, ding, ding, ding. So in terms of measurement model parameters, we're talking about factor loadings. We're talking about item intercepts and then item residual variances or error variances. In terms of structural model parameters, for structural invariance, we have the factor variances. We have any factor covariances if there's more than one, and then the factor means. So, all right, so there is a series of like well-known, everyone follows the rules steps for this. And there's a language that goes with it that you need to learn. So optional step 0, according to the literature, is to do an omnibus test of equality of the entire covariance matrix across groups. So a multi-degree of freedom, like constrain all the covariances, constrain the variances, constrain the means, all of that to be different, or constrain them to be the same, and then test the difference in log likelihood. And so this is, I would say, optional because if it holds, the idea is, okay, you have full invariance, go forth, you're done. But I don't think this is particularly useful. So for instance, if I have, let's say, 10 indicators, that is how many different parameters in a variance covariance matrix for 10? Remember the formula for this? It's on the bottom of the slide. So 10 times 10 plus 1, that's 110, divided by 2 is 55. So if I tested an entire covariance matrix, that's 55 things I'm constraining at the same time. It could be the case that a couple of those things really want to be different, but those differences are washed out by the other 42 that don't, or 52, excuse me. So I don't think this is terribly useful as a first step, and I don't do it, but I'm presenting it in the interest of completeness. Another potential debate is whether you go through these steps starting with the most complex model or starting with the most restrictive model. And I prefer to start with the most complex and work my way down. because otherwise you might miss something if you put all the constraints on first and start with the most restrictive model. So in this example, just for this slide deck, just to walk us through what the steps are, let's pretend that we have 6 items. They are measuring 2 factors, so 3 each, and we have 2 groups that we're looking at. So in terms of the total number of possible parameters, it is number of items times that plus 1 divided by 2, plus number of items again to get back to the means. So in this case, we would have 27 per group, so 54 overall. So the first step is called configural invariance, and that is the configuration of the factors. So do you have the same number of factors, the same pattern of free or fixed loadings, and do they have the same conceptual definition? In practice, you would start by estimating a factor model on each group separately and hope that they get to a close enough same place for you to be able to do this. So in this case, we would estimate both groups' models, but keep everything separate. So each group just gets its own model happening simultaneously. They're each separately identified as well. This will be as good as it gets in terms of absolute fit. Like, this has the most parameters out of everything. So everything we will do from this point forward is designed to test if the fit gets not worse. So you've done this a couple of times this semester, like when we tested tau equivalence in parallel items. In those cases, that's another example of a not worse. You're putting constraints on it. You're trying to reduce the complexity of the model and seeing if those constraints hold by asking how much worse the model fit got. I say absolute fit because when you're working with log likelihoods, they will always follow this pattern. If you put constraints on a model, it will either be worse or not worse. It can never get better. But for certain indices that are a function of parsimony, like RMSEA, it can. So RMSEA is offness per degree of freedom, which means when you give degrees of freedom back, your RMSEA can actually get better. So not worse is a distinction with respect to the chi-square and the log likelihood specifically. So last year I had folks be like, what does close enough mean? And I thought, that's a reasonable question. So I made some new pictures to illustrate this. So here's an example of when I would call it game over, do not pass go, do not try any further steps in this analysis because you're done. In this picture, I have a 2-factor model, each measuring 3 things, but what the factors mean conceptually can't be the same, because down here, it is item 1, 4, and 5 that define factor 1, but up here, factor 1 is 1, 2, and 3. So if you have something like this, even though it's a 2-factor model, it's not the same 2 factors. It wouldn't make sense to ask, for instance, if the loading for item 4 is the same as this loading for item 4 because they're pointing from different circles. So if you have something like this, there's really no point in doing any kind of invariance testing, which would mean there's no point in doing any kind of group comparison. Like, what these factors mean is not the same. So you're done. That's it. Here's an example of something you can work with. So this is a 2-factor model in which each factor is measured the same way in both groups, but the groups differ in whether it's 2 factors or 1. So the bottom group, basically this would be, I think it's just 1 factor. Like, the correlation is either 1 or close enough to 1 that putting that constraint on it wouldn't hurt, whereas it's much less than 1 in this one. Because you can set these models up this way, in group B, you can have them be 2 factors and just fix the correlation between them to 1 to make the model work. Then it makes sense to go through with the rest of the tests. So you would end up with different structural models, different factor covariances in this case, but you can essentially turn a 1-factor model into 2 by setting it up this way. You might have to watch out for non-positive definite solutions though, meaning that it's not going to like this constraint. So you may let it go, but watch for it to get crazy. And if so, you have to put it on there. So this would be, okay, go ahead and try it. But this one would say no. So configural variance is just like, do we have the same factors to start with conceptually? Then we go through and do a whole bunch of likelihood ratio tests to see whether or not the constraints hold. So if you're using the if you're using the robust version, you need the rescaled version of this test. Here's the information about that. It's in several slides throughout the CFA unit. I have a spreadsheet for it. I have spreadsheets that go with these examples that have this test built into it as well. So we are removing parameters and hoping that the fit gets worse or not worse. All right, there it is. I figured I threw it in here. So there you go. All right, so this is what it looks like. Configural invariance model would look like this for two groups, for two factors. So in total, we have 54 degrees of freedom possible, right? That comes from the number of means, variances, and covariances of these 6 items across two groups. We are going to spend 38 to estimate this model, leaving 16 left over as the model degrees of freedom. So where that comes from is, let's say that the left side of the page here is group 1, the right side is group 2. And at this stage, everything is separate. So the first subscript refers to which item the parameter is for, and the second is going to be which group. So all of these have 1s and all of these have 2s because everything is separate. That means that each factor has to be identified within each group. Otherwise, it's not going to work. So in this case, I would recommend fixing factor means to 0 and factor variances to 1 so that you can estimate all of the parameters, and you would estimate whatever covariance across the factors that you would need as well. So at this point, though, the groups are not on the same scale. Just because you set the factor mean to 0 and the factor variance to 1 in each group does not put them on the same scale. There will be a homework question about that at some point, I guarantee it. So, you're arbitrarily setting a reference for the model, but it's arbitrary in both groups. Not until you have constraints linking the item parameters together across groups do you have any kind of common scale. So we have 12 intercepts in total because there's 6 per group, 12 error variances in total, 12 factor loadings, no factor variances because they're fixed to 1 for identification, 2 factor covariances, 1 in each group, and no factor means because they are fixed to 0 for identification. Okay, with me so far? Zoomers, looking down at my camera. All right, roomers, looking up at you. Okay. So next step then, assuming that you have factors that are close enough in terms of they're meaning the same thing to go forward, is called metric invariance. It is also called weak factorial invariance, and it concerns the factor loadings. So the question is, do the groups have the same factor loadings or not? And this is not the same thing as a tau equivalent model. So within a group, we're not saying all the loadings have to be the same and all the items have to be equally discriminating. We're saying across groups, the loading for item 1 is the same as the loading for item 1 in the other group. The loading for 2 is the same as 2, and so forth. So at this step, we have to simultaneously free one of the constraints in the structural model. Otherwise, we're inadvertently making 2 constraints at the same time. So you will need to free the factor variances in the other groups and leave them fixed to 1 in the reference group, specifically. And here's a reference for why you should do it this way, but I will say it more simply. What's your alternative to fixing a factor variance to identify the model? What could you fix instead? And feel free to read from the screen, you know. What's the alternative to fixing a factor variance to 1 for identification? Yeah, fix one of the items. We call that the marker item or sometimes the reference item. So if I have 2 groups and I fix my marker item to 1 in this group to identify the model, and I fix the marker item to 1 in this group to identify the model, is that an identification or is that a constraint? Let me put it this way. Is 1 equal to 1? Yeah, right? So you are saying not only that you have identified the model using item 1 as the metric, but you're saying that item 1 has the same factor loading in both groups. So that's a constraint. You don't want to do that. So to avoid that problem, then we fix the factor variances to 1 in the reference group, free them in the alternative groups, and then we can test all the loadings. And this is what it would look like. So we have now spent 34 parameters instead of 38 for a savings of 4. So where does that happen? We still have 12 intercepts, we still have 12 residual variances, we still have 2 factor covariances. Where it happens is now 6 loadings instead of 12. So now the second subscript on the loadings is gone to indicate that this is a constraint. So item 1 is supposed to work the same way in measuring factor 1 as it does in group 1 as it does in group 2. So 6 loadings, how many did we have before? Throwing softballs. 12, yeah, 6 times 2. So why am I only saving 4 degrees of freedom? Yeah, I pick up 2 factor variances is why. So there are 2 different factors in each group, which means that it is the factor variances in group 2 as the alternative that need to be estimated. Factor means are still 0 because we still have not constrained the intercepts. So this model is halfway on the same scale across groups. It's on the same scale with respect to its loadings and its factor variances, but it is not on the same scale with respect to its means and intercepts. Halfway. So why do you think we need to free the factor variances? Let me ask that. Any thoughts? Impressions, I should say. I like that one.
So for identification, don't we need to fix one of either the factor variance or the item loadings? We cannot fix both at the same time.
We should not fix both the factor variance at the same time as the loadings at the same time, yes. And my question is, so are you, this because it's a double constraint? Is that your answer? Yep, I'll take that answer. Groups might have different distributions of factor levels. I'll take that answer too, yeah. So it is entirely possible that groups have different factor variances, that one group is more heterogeneous. And so you're not allowing that to happen. So you're allowed to see if that is the case after the loadings are constrained equal, because then the 2 groups are sharing a common method of identification in that the factor variance is fixed to 1 over here, but the loadings are tied together. So they're all being put onto the same scale with respect to variances and loadings. Another reason is if you think about this as a slope, right? A factor loading is fundamentally a slope. It is the change in y for a 1 unit change in x being the factor. So if a group has more variance in their factor scores, then the slope needs to change because of that. So you would expect different slopes potentially if it's the factor variances that want to be different. So if we allow them to be different, then the question is, do the slopes still need to be different across groups or not? It could have been just because of differences in what a unit is in terms of x for the change in y for a 1 unit change in x. Okay. So then the question is, does this fit not worse? If it fits worse, double check that you set it up correctly. Always, that's the first step. The second step is to figure out then why it fits worse. And we are going to be using modification indices for this. However, I think that they are not cheat codes in this situation. What they are going to tell you is which of your constraints is hurting your model. It will tell you how much your chi-square would improve if you released the constraint on each loading. So this can tell you where the problem is in terms of why the overall model fit comparison might have been significant, which loading or which loadings. So that brings us to a new vocabulary word, partial invariance. So you would release the constraint on one loading, retest, and see if it's still not worse. And you can go through this up to like one item. One item is what you need mathematically to make this work, to have the loadings be invariant. That's a terrible idea. How much is partial? Meh. I would like to say most of them should be invariant. If more or not invariant, if more want to be different than want to be the same, that's not good. But this also allows for differences in measurement that are on purpose. This idea that not all the loadings have to be the same. So for instance, what if an item is not relevant in one group? I heard an example of this during a job talk where someone was talking about cultural differences in parenting, and there was an item on the survey about how often you put your kids in timeout. Well, she was researching a particular group that was like, what the hell is timeout? We don't have that. We don't do that. And so that question is not relevant to measuring whatever parenting trait within that group. Okay, don't ask it. Don't measure them. Don't give that item to people for whom it's not useful, and then just not have the constraint. So you can have different items across groups so long as you have some in common and their properties are enough the same that you can link them together. You don't have to have the same items in every group. So functionally speaking, it is as if you have an item whose loading is different across groups, it's as if it's a different item entirely. Like from a measurement point of view, it's a different item. Even if it is literally the same item, it just behaves differently, it's a different item. That allows you flexibility in which particular items you're going to administer. And I would argue that full invariance, even if the likelihood ratio test is not significant, I would still check the modification indices. Because it could be that you have, 7 loadings that are great and one wants to be different, but the net total of that is non-significant, and I wouldn't want to miss the one. Okay. Good so far? Good still? Stretching. Stretching is good. Next up, after weak comes strong. I did not make up these words. Okay, this is the literature. I want to say the 90s maybe, give or take, is when this stuff starting becoming a thing. So scalar invariance or strong factorial invariance is for the intercepts. So the way that this is typically administered is like a single elimination tournament. If an item loading fails, then it's kicked out of the tournament. And so you would not typically test intercept constraints on items that have already failed metric. They're just done. That's traditional. If you don't have very many items, though, I might try it anyway, just to try to hold it together as much as possible. And scalar invariance is required for factor mean comparisons. So once you put on the constraints for the intercept, then it's the same idea. We don't want to put a structural constraint at the same time. We want to free the factor means in the alternative group and keep them fixed to 0 in the reference group for identification. And otherwise, if we fixed an intercept to 0 for identification, that would be a constraint. So this is the part of the course, by the way, where the distinction between mean and intercept is really, really important. Okay. So it is the case that if you identify your model so that the factor mean is 0, then the item intercepts just become the observed item means. That is the case. And that is how I knew for some of you in your homework that your plot was messed up. The lines for the factor response plot, the point for 0 needs to be the same intercept as given in your table, and if it's not, then something went awry. Because I know what the means are supposed to be, I know what your intercepts should have been. However, it is not a constraint on the item means that we are making, it is a constraint on the intercepts. The difference is conditionality. An intercept is the expected response given a trait of 0 specifically. So you would want the intercepts to be the same even if the item means differ across groups. What you want to be able to say is that the reason that the item means differ across group is because the factor differs across groups, and the factor is what is driving those differences. That's what we want to be able to say. The reason the item means were different is because the factor means were different, but once you control for that, by letting the factor means differ in the alternative groups, if there's more than one, then you can see if the intercepts still need to differ or not. So intercepts is the idea here, not means for the item responses. So that would look like this. So we've got, again, 54 original degrees of freedom based on the number of means, variances, and covariances of these items across groups. We are now only spending 30 for another savings of 4. So by constraining all of the intercepts to be the same across groups, and then adding the 2 factor means so that we allow factor mean differences instead, we save 4 degrees of freedom. Can I say all of that again? Yes, I can try. So in this equation, these are intercepts, and you can see them that way, right? Like this is the expected response if the factor score is 0, in which case this would drop and this is all that's left. So even though these numbers are the item means, they are intercepts because they are conditional on a factor score of 0. So it is perfectly reasonable and expected for groups to have different item means. The question is, once you allow the factor means to differ, do they still need differences in the intercepts? What we want to be able to say is that differences in the item means across group is due to differences in factor means only. And then otherwise, there's no differences in the expected response for a trait score of 0. Okay, is that better? Not quite. I said it again, though. I'm trying. We'll see examples of this because the example that your textbook uses actually has a scalar invariance problem for one of its items. So here's the picture that goes with this idea. So box A describes a plot in which the x-axis here is the trait, the factor, and the y-axis is the expected item response. So he's using x's in his books for whatever reason. And these two lines, the slope of them describe the factor loadings. So the fact that these are parallel lines indicates metric invariance or weak invariance, equal slopes, equal loadings, as does this picture, parallel lines. The lack of a distance between them, conditional at a trait level of 0, if this is where it's indicated here, indicates scalar invariance. So at a theta of 0, at a trait score of 0, there is no difference in the expected response based on whether you're in group 1 or group 2. That's the idea of scalar invariance. In the picture B on the right, there is a large difference between groups and their expected response, even at the same point on the trait. So there's something else that's causing people to answer the question differently if they're in group 2. What that is, who knows, but it's something else. It's not the trait. The D picture here describes an item for which metric invariance, the loadings, and scalar invariance, the intercepts, does not hold because the lines are not parallel. That's the metric part, and there's a big gap between them. And he made this picture here for the case of not metric, but yes, scalar invariance. And I was like, really? I guess because this distance is not that big? But the other way I prefer to think about it is, what if you changed where 0 is? If 0 were over here, in terms of the factor, then maybe I would say that there is scalar invariance, because at this point, they're not that different. But this illustrates why the single elimination tournament rule exists, because if you have different loadings, that can create different intercepts for that reason only. Non-parallel lines mean the difference between these is going to change as a function of the x-axis. So there may be points on x in which the groups are equal, and there may be points on x in which they're unequal. Non-parallel lines are the problem. So if your item fails metric, meaning the loadings do not want to be the same, it is traditional to not test scalar for this reason. But you still could. There's nothing wrong with it, but if it doesn't hold, it could be because metric is the problem. That's all. All right. Yeah, so scalar works the same way. Do the likelihood ratio test, see if it fits, not worse. If it does fit worse, go see why. Go see which intercepts want to be free and which ones are happy being constrained to be equal. And you work your way towards partial scalar invariance. So the thing with this is that if you're interested in factor mean differences, any items that don't have their intercepts constrained do not contribute to the factor mean. So it's not really the factor mean if you have partial invariance. It's the mean with respect to the items that are held equal in terms of their intercepts. So it's not quite the same in this case of partial scalar invariance. But it does also indicate that you can have different items for different groups and have their intercepts be non-invariant if that's needed. Last step of measurement invariance, error variances. This is called strict factorial invariance. Weak, strong, strict. And this is asking the super important question of whether the amount of variance that's not the factor is the same across groups. If it isn't, I don't know, who cares? It's part of the process though, and if you don't do this part of the process, that can cause problems in the other aspects of your model. Research has shown, so we go through it anyway. This one, though, does not have a structural model correspondence. You don't have to free anything in the structural model when you test error variances. So when you free loadings, when you fix loadings, you free factor variances. When you fix intercepts, you free factor means. When you fix error variances, you're done. There's no analog to the structural model that goes with it. You would also do error covariances if those exist. So at this stage then, if I were going back to my picture, the E variance that goes with each of these is what is being constrained. So the E is the specific residual, its variance is the parameter we care about, and in this case we're saving 6 degrees of freedom because we have 6 per group and no factor parameters being added. Same process, check to see if the fit is not worse, check the modification indices if it is and see why, and then let those go that need to go, and then you're done you're ready to test structural invariance. Hooray! Okay, do you want to see an example? Why not, right? Numbers usually make it better, usually. So the first example, I have 4 examples for this unit. And this is the first one, is the ideal scenario. I'm pretty sure these data are fake. If they're not fake, they are based on real data and they were simulated, like they've been messed with. How do I know? Because there are exactly 345 people in each group. That's not going to happen. And by the way, if you have a great asymmetry, like if you have 1,000 people in one group and 100 in the other, then you will have less power to detect differences than if you have more equal group sizes. It's the same idea as in the rest of statistics. Here's another reason I think these data are fake. They're measured on a 9-point scale. You don't see that very often in practice. But these are supposed to be indicators of depression. So here are the indicators themselves, and people they're rated on a scale of 0 to 8 in this case. Now I have a disclaimer over here. Starting in M+ version 7, and I believe, yeah, there's a thing, I found it in the our corresponding SemTools package. There are automated routines to do all of this for you. In the analysis section, you can say test metric, scalar, and this, and it will do everything for you. I am deliberately not showing you that because that process does not help you when you find non-invariance. If everything works perfectly, it saves you a lot of time, but nothing ever works perfectly. And I will say that of all the materials that I have for my courses on my website, by far, invariance testing is what I get the most emails about from people who have found my website and found these materials. So apparently there is still value in doing things the long way, so to speak. So I'm deliberately not showing you the shortcuts, but I'm letting you know they exist. It's funny to me because I don't study invariance. Like, I just learned how to do it. It's not a research area of mine, but like, I've given a lot of advice on it for reasons that, you know, who knows? Probably because I'm nice enough to write back. That could be the reason. All right, so in terms of new parts of the code here, the setup for this is going to be the same. I'm just going to show you the different models as we go. Here is the new thing. Grouping. I believe you can type group for short. It wants to know which variable in your data set is responsible for denoting the group membership. I believe it is an option to read in 2 different data sets, but I'm not 100% on that. I've always done it this way. So in this, we have a person ID variable. They're using gender as the example here, so we have a variable called sex, and then items 1 through 9. And so in this analysis, they're treating gender as binary, and we have women as the reference group. I'm using MLR estimation, and I'm asking for all the usual output. By the way, this right here, I don't know if you've seen this before, in mod indices, that is the cutoff for printing them. And that number is for the chi-square that would result if you added that parameter. 3.84 is the cutoff for alpha of 0.05 for 1 degree of freedom. That's why I put it that way. So I'm only asking it to show things that would improve the model significantly. You can change this to be whatever number you want. Sometimes I throw in 6, which is closer to an alpha level of 0.01. So then this will be the same across all the models, and it will just be the model part that changes as we go. So the key idea in reading this syntax is that what's going to happen for the reference group is going to stay the same the whole time. Their code is going to stay constant. What's going to change is what happens in the alternative group code as we turn things on and off. So right now, I have labeled all of the parameters from the reference group. So I have L1 to L9 for the loadings, I1 to I9 for the intercepts, E1 to 9 for the error variances, and then I have an error covariance right here that was included as part of the original analysis, which I've labeled as ECOV12. Depression is my trait, but I can't name it depression because I can only have 8 characters, so I fixed the factor variance to 1, and I fixed the factor mean to 0. Over here on the men's side, everything is exactly the same, except no labels. So the labels are what's going to get added at each step, and they will become constraints if you give the same label to the same parameters across different groups. So this is my configural model. This is as good as it gets. Question?
Yes, so these two models, are we going to put the two models in the same syntax?
Yes. So this one is first, and it will be blue, and then this comes second, and it doesn't turn blue. But they're just stacked on top of each other.
But in the main model, there is no indication of we are working with men now.
Yes, you would not know that this is for women. There's a couple different ways that you can set this up in M+. In this version, it's like there's an assumed reference group, and this is just telling you how the alternative group is going to differ from the reference. And so the label here then is part of what you would tell it. Otherwise, it wouldn't know which model is which. So if I had 3 groups, then I would have to have a name here and then another model with a different name for the third group underneath it. They would all be stacked in the same syntax file. And just as a reminder, all of these files are online because this is textbook data. I was able to run it and give it to you. So within, there's a download folder that goes with this example with all the original files, so you can see what it looks like. All right, so this is configural. This is as good as it gets. It better fit well. Otherwise, there's no point in going forward because everything we do from this point is going to try to make it worse and break it. So number of free parameters is 56. How did we get to 56? We got 9 items. How many factor loadings do we have? 9 per group. 18 factor loadings. How many intercepts do we have? 18. How many error variances do we have? Okay, what's 18 times 3? 56? Actually, not quite. Close to that. We also have an error covariance, so 2 more. But we don't have any factor model or structural parameters because factor variances are both fixed to 1, factor means are both fixed to 0. So we get a couple new things on the output. This is new. It says chi-square contribution from each group. So this tells you for the combined chi-square across the 2, how much of that is due to each group. So you can interpret this as like a group-specific fit, except that if the groups are different sizes, these numbers have to be different. So in this example, because the groups are exactly the same size, I can say it looks like the model fits better in the W's or the M's. The W's have 50, the M's have 43. Model fits better. Do we want chi-square to be big or little? That's the question. Got 1 vote for W. No one else wants to vote. 1 vote for M. As a reminder, the chi-square is telling you how much worse than perfect your model is, right? It's the likelihood difference in height for the saturated versus the current model. The M's win. They're lower in this case. W and M is what I'm using, because that is what I said, actually, right here. I think this should be, I'm going to type it out, because I probably changed it and forgot to change it. How's that? There, it's been fixed. Problem solved. There we go. Otherwise, though, my chi-square is significant. Yeah, I know, it's going to be. It's just never non-significant. That's just unreasonable. How about RMSEA? What does it think? Thumbs up or thumbs down for this model? RMSEA of 0.047. It's pretty good. What about this p-value? It's non-significant. Is that good or bad? It's bad? Or is it good? It's backwards from how you're used to thinking about p-values. This is the test of close fit, the test of whether the RMSEA is less than or equal to 0.05. So a non-significant result in this context is a good deal, because it means that we passed the test of close fit. It is not different than 0.05. It is actually less. The confidence interval includes 0.05. That's another way to say it. So far so good with respect to model fit. Let me zoom over to the other column. CFI and TLI, are they happy? 9.6 and 9.5? These indices, as a reminder, tell you how much better your model is from the worst possible null model with no covariances. And these can be low if your null model is actually close to your model. If you don't have much covariance in your data, then these are not going to be really good at tracking fit. Okay, so far so good. It looks like this is a good enough model to go forward with. I made a picture for you. So this is a plot of the unstandardized factor loadings. Now, we can't compare these because the models are not on the same scale. However, we can look for proportional differences. If all of the loadings for women were larger, that could have been because they have less factor variance, the difference in what a unit is that the slope applies to. If you see a mixture of some that are larger and some that are smaller, then that would negate that explanation. So this is somewhat of a foreshadowing as to what we should find. It looks like in most of these cases, the factor loadings are a little bit higher in women, or equal, but not all, certainly. So here's the output. So there is a new heading right under your unstandardized results that tells you which group you're looking at. And I have, by the way, an example using Lavon that goes with this if you want to look at that. I'm not covering it, but I can help you with it if you have questions. So here are the 9 factor loadings within the women, and these are the 9 factor loadings within the men. We've got residual covariance within each group. Looks like it's stronger in the men for whatever reason. Different intercepts across groups and different residual variances across groups. So it's the same factor model, but just all the parameters get to be whatever they want. Okay, what do we do next? What's after configural? Metric, otherwise known as weak. Yep, that's weak. By the way, in the write-up that goes with this, I always put either in a parenthetical or in the sentence what parameter is actually being constrained. I don't assume that my readers will have memorized this vocabulary. So metric invariance, i.e. factor loadings, right? Just help your folks along. Okay, we're going to play spot the change in the code. Here's my new model. What did I change to enforce metric invariance? Yeah, here's one thing. So the left side is exactly the same, and it will continue to be exactly the same. It's the right side that's going to change. Yep, we added a label on the factor loadings. Now note, it's L1 to L9 over here, it's L1 to L9 over here. So this is not just a label, it is a constraint. If I used a different label, then it would not be a constraint. Also, if you accidentally reuse labels, you will end up making more constraints than you meant to. So whatever naming system you come up with, it needs to be consistent. Is that all that I changed, or is there anything else? Yeah, I tried to put it in capital letters to help you out, because I knew I was going to do this. Factor variance can now be freely estimated in this group. Otherwise, we'd be putting a structural constraint at the same time as a measurement constraint, and we don't want to do that. So previously we had 56 parameters, now we have 48. So there's really one thing of interest here. Did the model fit worse? And I did this in the spreadsheet. Degrees of freedom 8. The chi-square for the difference in log likelihood, the rescaled log likelihood, I should say, is 4.26 with a p-value of 0.8. So we did not make it worse. That means metric invariance holds. So the way that the item relates to the trait in terms of its slope is the same across men and women for all 9 of these items. The model fit should still be good, but look what happened to RMSEA. It was 0.047, now it's down to 0.042. It's happier because we're spending fewer parameters to get to the same level of fit. CFI and TLI are also a little bit happier. So the worse not worse thing refers to the chi-square test specifically. The others are on different reference points. I plotted the intercepts here. So the question then next is, it looks like for most of these women, most of these items, that the women have higher intercepts. The women have higher item means. So the question is it because they have a higher factor mean? Are they more depressed? Such that this is why you would see these specific item differences. We can find that out by doing scalar. So here's the results for the metric model, and you can see that the factor loadings are all equal across groups. Always check your output, by the way, to make sure that M+ did what you asked it to. Sometimes you can have typos that you don't notice and it causes the model to run, but it didn't do what you intended with your constraints. So I would eyeball these across your groups and make sure that they are in fact the same. However, at this stage, are the standardized loadings going to be the same? These are unstandardized. You think the standardized loading should be the same too, or no? Nope. I even said it right here. Always feel free to read from the screen. That's usually the answer is in the screen somewhere. But why not? Why aren't the standardized loadings going to be equal across groups yet? What else goes into a standardized loading? How do you standardize something? Error variances. They're still different. So standardized loadings will not be the same unless the loadings and the error variances are constrained equal. We're not to that stage yet. In terms of the factor variances, it does look like there is less variance in the men group. I think I said that backwards. Yeah, there's less variance. So in the reference group, the variance is fixed to 1. It can be estimated here. So the exact numbers don't matter. They're just setting the scale of the model, but you can interpret this as less because it's less than 1. All right, residual variances still differ as well. And scalar. What did I change? Scalar invariance is up next, testing differences in intercepts. Constraints on the intercepts for men. Ding, ding, ding. Right here. And what else did I have to do because I put those constraints on? Move my mouse out of the way. It did. I estimated the factor means. Yeah. This thing right here. So you haven't seen one of those in a while, probably. But now we are asking the question, do these groups have the same expected item response at a trait level of 0? We're allowing differences in the trait means so that it's not a structural constraint at the same time. So in terms of the result, it looks like, yeah, we can constrain the intercepts to be the same. P-value is not significant. However, I looked at the modification indices. I did that for the first model for the loadings as well. And I'm only showing you the ones that have to do with the constraint that we just placed. So I'm ignoring all of the others related to error covariances and cross-loadings and any of that kind of stuff. I guess no cross-loadings in this model. But this is telling us which parameter would result in an improvement in the model. And it's highlighting item 7 in particular. And it's telling me my chi-square would improve by about 6. Well, the chi-square test itself had a test statistic of 12. So that means half of the difference in fit is because of item 7 alone. That to me indicates a problem. And it also tells you what you can expect in terms of the new results. So it tells us right here, the expected change, this one actually, the expected change. So if we free the intercept, then the women intercept would be higher and the men intercept would be lower. And I wrote on here, just as a point of interest, item 7 is feelings of worthlessness and guilt. So needs to be different is never the end of the story. Needs to be different how is what your reader would want to know. And it looks like, if I were to try to put this in English, that conditional on the same level of latent depression, women are more likely to say that they feel worthless or guilt. So something else that is related to gender differences is causing different responses in this item besides depression. That's what it means. So on the whole, it looks like men are less depressed. They have a negative factor mean, and this is relative to a factor mean of 0 in the alternative group. So it looks like we do have some structural differences beyond just the differences in the items. So if we fit a partial invariance model, we'll do that, and that'll be our last one. How's that sound? Here's how I fixed it. I have item 1, or intercept 1 through 6 still, and then I added a different label in the middle to free 7. So if you forget the label, it will yell at you because it's expecting 9 labels. So you can't just omit it. You just need to change it to something else. And I put a lowercase m on here because we're in the nil model. So in terms of the output, here are the new intercepts for item 7, and lo and behold, this is what happened. Women have a higher expected response, conditional on a trait of 0 for that particular item. And our new likelihood ratio test was cut in half, just as we predicted. So this is an improvement to free item 7's intercept. That's what this test is asking. This one means that we are still in good shape with respect to our comparison of metrics, so not worse. And there's no more modification indices with respect to the intercepts, so we're good to go there too. All right. See, not so bad, right? Just a whole shit ton of model comparisons. That's the worst part about it. So this is probably where, if you have the chance to work in Lavaan, you would have an advantage in terms of the efficiency of doing this, because you can run the ANOVA command and it will do the likelihood ratio test for you. There is no analog in M+. So that's why I have a million spreadsheets. All right, questions? Looking at the Zoomer windows and the chat. Rumor windows? No? All right, then let me know if you need anything. Homework 4 is due tomorrow. got office hours tomorrow in case anyone needs to have last minute help. Thanks for being here. If you guys are going to a conference on Thursday, have a great trip. I'll still be here. So, be safe. Thanks for being here. See ya all on the other side.